Morning, Doc.
Good morning, doctor.
Okay, so we'll continue together chapter 4. We still have just a small part on it. Do you see the PDF now?
Yes, doctor.
Okay. So last time you were doing this problem. So the slab is subjected to 4 parallel forces. Determine the magnitude and direction of the resultant force equivalent to the given force system and locate its point of application on the slab. So here you have a plate and it is subjected to several forces, but all forces are in z direction, okay? Because all forces are in z direction, then you can say that you can be sure that you can reduce your system to a single force. Why? Because we will see that now these forces cannot produce a moment about z. They can only produce moments about x and y. So the first step to do is to reduce the system to point O. This is the first step. And second, I move my force in a way to reduce to a single force. So let us start by the first step. For the first step, I do the force summation. I have minus 500, minus 600, minus 400, plus 100. I get a total resultant force of 1,400 Newton down. The second step is I will reduce to moment about O. Now, here, in general, I said in 3D, it's easier to do the vectorial formulation. But here, no need for the vectorial formulation because look, the forces are very simple and they are all along Z. So what I can do, I can find the resultant moment along X and the resulting moment along Y. Since, as we said, no moment about Z because all forces are parallel to Z. So I will start by doing summation of moment about X. As you can see, you have two forces passing by X-axis. So you have here 600 Newton and 500 Newton passing by X, so no moment. For the 100 Newton force, if you look at the moment of it, it can produce a moment about X and about Y. Now we are interested with the moment about X. What is the distance between the 100 Newton force and X, the perpendicular distance? Look, when I have a force, when I have a force along Z and I want to find a moment about X, the distance will be along Y because the distance should be perpendicular to both, to the axis and to the force. Okay, so here the distance between the two is this one, which is equal to 5 meters. So the magnitude is 100 times 5. And what about if it's positive or negative? What should I do? I should do the right hand rule, okay? If I put my 4 fingers along the force, okay, then if I do the right hand rule, I will get my thumb pointing in positive x direction. So this means that I have a positive moment. So it's plus 100 times 5 along x. Now, for the second force of 400 Newton, the distance is the perpendicular along y, which is 10 meters. And if you do now the right-hand rule, you will see that it is a negative moment, because it is opposite, the force is opposite to the other one and from the same side of x. Okay, so if you do your sum like this, you will get that it's a negative moment. Okay, so it's minus 400 times 10. And in total, if you calculate the resulting moment about x, it is equal to, you get your result. Now, why here if you want, the problem when you asked me questions about this problem was this term. Why they put minus 1,400? Okay. To understand why, the total moment you will get, okay, is a negative moment, because you have plus 500 minus, no, we have, yes, 100 times 5, yes, plus 500 minus 2,000, minus 4,000, because it's 400 times 10. So it's a negative moment. Because it's a negative moment, then when you displace your resulting force, it should also have a negative moment. Okay? So what you were able to do now, you was able to reduce here at 1 force, Fr, and you got a negative moment along y, negative moment, sorry, along x. Okay, so now, because it's a negative moment, how you should displace your force, your resultant force, if you want to produce the same effect, you should have your force displaced in a way to produce a negative moment. Okay, of course, when you move your resultant along x, nothing will change concerning to moment about x, because displacing your force along x will affect its moment about y, but not its moment about x. Okay, so to be able to get rid of this couple and to replace your system by a single force, you should move the force in a way to produce the same couple about x. And since it's a negative couple, okay, you can try the right hand rule. You should move Fr in positive y, not in negative y. This is also, if you want, it is completely physical, because all forces are on the plate. يعني منطقيا the resultant force should also be on the plate. يعني أكيد ما حنرجع لورا. But to be sure that your calculation is true, you can do the right hand rule and see that when you displace in positive y, Fr produce a negative moment about x. Because if you do the right hand rule here, when Fr is downward, it will produce a negative moment about x when I move in positive y. Okay. Now, what should be the distance y? This is why here they put a minus, because the moment of it is negative. So it's minus 1,400, which is the magnitude, times the positive y distance to displace. This should be equal to the resulting moment about x. From here, you get that y should be equal to 2.5 meters. Okay? Now, we'll do the same about y-axis. So first, we should calculate when the force was here, what was its moment about y. Then we choose what distance x to displace in order to have a unique force without any cut. So now, for the moment about y, the 500 Newton force is not producing a moment because it's passing by y. The 400 Newton force also. So you just have the moment of the 600 Newton force and the 100 Newton force. So now for the 600 Newton force, if you do the right hand rule, it's a positive moment, because if you put your hand like this, okay, and the palm of your hand facing y-axis, you will get a positive moment along y. So it's a plus 600 times the perpendicular distance. This is the perpendicular distance, this one, and this distance is equal to 8 meters. So it's plus 600 times 8. While for the 100 Newton force, it's a negative moment, because if you put your right hand like this, it will give you a negative moment along y. So it's minus 100 times this distance here. This distance is the difference between 8 and 2. It's 8 minus 2. So it's 6. So it's minus 100 times 6, as you can see here. 600 times 8 minus 100 times 6, and the other two are 0. Now, once I find it's a positive moment along y. So now I can put that the moment vector about y is like this, and it is positive. Okay. So now all I have to do is to try to move my force in order to produce the same moment. Okay. And as you can see, since the moment is positive, I should displace in positive x in order to create this moment. Because if I do the right hand rule, when I displace in positive x, if I put my hand like this, then it will produce a positive moment about x. And this is why here it's a plus. So plus the resulting moment along y. Here, guys, we have a certain, yes, here, this is the magnitude of the force. So plus the magnitude of the force times the distance, which is x, okay? So the only unknown is x. We get that the value of x to displace is 3 meters. So now, once you displace your force by x and y calculated, you don't need any couple. You reduce your system to one equivalent force. Any question on this? Okay. So now we still have one final part in this chapter, which is reduction of a distributed load into one equivalent force. Okay. So in many cases, we have a situation where a body is subjected to a distributed load. What do we mean by distributed load? In general, until now, we have considered forces acting at a local point. So we call them concentrated force. While sometimes you have several actions that can be distributed on a surface. So for example, the wind action, the wind is acting on the whole surface. So in general, we express, when we have, for example, a load on a surface, then we express the load as Newton per area, Newton per meter square, for example. Other examples is the weight of a body. Of course, in general, when we work with the weight, we just represent it at the center G of the body. This is the resultant, if you want, of all these forces. But in reality, it's a distributed load because it's acting at several points. Each elementary mass, because each elementary mass has its own weight. But when you do the summation, when you reduce this distributed load into one force, you will end up with the total weight at the center of gravity G. Okay? So in this part of the chapter, we will learn how to reduce a distributed load into one equivalent force. Now, to start with, let us consider a general case. If I have a distributed load, as you can see here it's a linear load. So when it is distributed on a line, we call it linear distributed load. And its unit will be Newton or kilonewton per unit length. So here it's kilonewton per meter. While if it is distributed on an area, we give it in Newton per meter square. Okay? So here, I have a linear load acting on my system. And I want to find first the total force due to this distributed load. Okay? So first, as you can see, since this distributed load is per unit length, to obtain the force, we should multiply by a length. But because W is changing with X here, what we should do, we should divide this load into small parts, very small parts. Okay? For each part, I can calculate the elementary force. How I can calculate the elementary force for each part? For each part, if I know the length, so since I will take a very small length since omega is variable. So for example, here at this point, I can read the value of omega x. Okay? And So omega x represent what here? Represent the height. This is omega x. Okay. This is omega of x. And dx is the elementary length. So here, a very small thickness. I considered a very small thickness dx. Then my force represent what? My elementary force. dF is equal to wx, which is in force per unit length, times dx. Okay? And as you can see here, you have infinity of elementary forces dF. So if you want to calculate the total force, what should you do? Like in math, when you want to calculate total area and divide it into small areas, you do integration. Okay? So here to find the total force, you should integrate over the total length. So here you should vary dx. X is varying from 0, which is the first point, to the coordinate of the last point. So if we consider a total length L, so we are integrating over L, omega x dx. So if you want to put the limits of integration, you should put here. It is from 0 to L. Okay, and this will give us what? When we integrate from 0 to L omega x dx, mathematically, this will give us the area under the curve. Okay, so we can say from here what we can deduce. We can deduce that the equivalent force from a distributed load is equal to the area under the curve of the distributed load. In general, in this course, we'll give you simple distributed loads, مش complicated one with variables. In general, we give a known geometry. So if I give you, for example, a rectangular load, okay, then directly you say the equivalent force is equal to the area of the rectangle. So no need for integration. You calculate the area. Okay. Now, once we found the equivalent force, you know that to reduce a system, it's not enough to find the resulting force. We should also find its moment. Okay, so let's say we should choose a point to reduce at. If we choose O, for example, then we should find what is the resulting moment about O. Because when I reduce a system, okay, I will reduce it to one force, one couple at a point. And after this, I can move the force in a way to create the same couple. So here, if I consider for each elementary force, what is the moment about O? So if I take a small force here, okay, for each elementary force, dF, we have seen that dF is given by what? It's calculated by omega dF. Okay. Now this force is producing a moment about O. To find this moment, I should multiply by the distance. What is the distance between the force and O? The distance is x. Okay. So I should multiply by x. Now, is it a positive or negative moment? I can choose a positive direction. If I consider the clockwise as positive, so here all my elementary forces dF will produce a positive moment about O. This is why I can say that the elementary moment dm, what I mean by elementary moment, the moment of a small force dF, is dF times the distance x. Okay, of course I'm getting moment about O. And if I replace dF by its value, which is omega dx, I end up with x omega dx. This is the elementary moment about O. Now, if I want to find the total moment, the resulting moment, what should I do? I should do integration. I should integrate and say that the resulting moment is integral x omega x dx over L. So from 0 here to L. Okay? So this is how I get the resulting moment at A, M result. Now, once I find M resultant at O, I end up with the following. I have a downward force at O, F resultant, and I have a clockwise moment, M resultant at O. Now, can you tell me, how can I reduce my system to a single force? What should I do with my force? How should I displace it first, in positive x or negative x?
Positive x.
Positive x. Because to produce a clockwise moment, I should move my force in positive x. Now, what should be the distance to move it in order to get an equivalent system? I should have that the moment produced by this force should be equal to the resulting moment MRO. So what is the equation I can write? I can write that MRO should be equal to the distance d, which I move my force, d times F resultant. Here they call it x bar. I will tell you why they called it x bar. So now let us replace d in the by the terms of MRO and FR. D is MRO over FR. And we have seen together that MRO is integral x omega dx. So I replace MRO by its value, which is integral x omega dx. And I replace F equivalent by its value, which is integral omega x dx. Okay, what do I get here? If I look well at my formula, we said that omega x dx is represent an elementary area here under the graph. So I call it dA. So I end up with integral x dA over integral of dA. This formula reminds you of something? Integral x dA over integral dA. It represents what, this formula? You remember the formulas for centroid of an area? How you calculate the centroid of an area? I don't know if you know it, but I think you should know it. Okay, I will repeat it anyway. If you have any area and you want to find its centroid, okay, then the x bar is the coordinate in x of the centroid, and y bar is the coordinate in y. And to be able to calculate them, if you have a function, variable function, you can say that x bar is integral x dA over integral dA. Okay, so this formula represents will give you the position of the centroid of your area. So what can I deduce from this? I can deduce that if I have a distributed load and I want to replace it by one force, okay, the first conclusion is that the force should be equal to the area under the curve. And the second conclusion is that the force should pass by the centroid of the area. Okay, so this information will allow me to reduce simply my forces without the need to do any integration, because we will see together that I will give you simple geometry, rectangle and triangles. So no need to do integration. Just here the integration for you was to understand why we replace a distributed load by a force equal to the area of the under the curve, and why it's passing by the centroid of my system. Okay, so let us practice this together. You will understand it better. Any question before I start problems on this? Okay, so let us do an example on this. Okay. A nice house is sitting on top of the ice, and the wind is gusting out at a speed up to 40 miles per hour. The wind load is approximated by the distributed load shown. Calculate the total force that the wind exerts on the ice house and the point of application of the equivalent force. So as you can see here, you have a house subjected to wind action. So of course, under the effect of wind, you will create a distributed load on the wall. Okay? So since I have a distributed load on the wall, I will try to reduce it. They asked me to calculate the total force and to find its point of application for the equivalent force. Okay? So if you look at the figure here, you have that your distributed load here is divided into two parts. A rectangular part, so here you have a rectangle, and a triangular part with this triangle here. So whenever you have several geometries, what you should do first separation of your geometries, and for each one, you can reduce each one to one force. Okay? Let us start by the rectangular load. We said that a rectangular force can be reduced to a force equal to the area under the curve. What is the area here? It's the area of the rectangle. Okay? And it should pass by the centroid of the rectangle. So first, the value of the rectangular force, which they called it F uniform because omega is constant. Okay? The value of F is equal to the area of this rectangle. And the area of this rectangle is 40 times the height. Here, this height is equal to h over 2. So it's 8 over 2, it's equal to 4. Okay? So here, since I have 4 feet, and look, no need to convert units, keep the same units. So here, this is 4 feet, and this is LB per feet. So you will end up with 40 times 4. The result will be in LB. So first, this force is equal to 160 LB. Now we still need to find its point of application. As we said, it should pass by the centroid of the rectangle. So you know that the centroid of the rectangle is just here at the middle. So if I consider this is the force, then it should pass by G. So the distance from here will be equal to 4 over 2 equals to 2. So now, since it's at 2 feet from the top, and the total height is 8, then if I consider the bottom point O, it should be at 6 feet from. So until now, I have reduced my force, okay, into my rectangular force into one force. I still need to look at the second force, which is the triangular force. Just let me check here. Okay. Now, for the triangle, I want to do the same job. So first, I should calculate the area of this triangle in order to find the resultant force. Okay. So the area is equal to the height here, which is also 4, times the base. I have this distance equal to 40. So it's 40 times 4 over 2 for a triangle. So I get 80. Okay. So the triangular load can be reduced to a force of 80 lb. Now I still need to know its point of application. You know also that for a triangle, what is the position of the centroid? So here, let me clear everything. Here, whenever you have a triangle, okay, this is your centroid. You have a property for the centroid that if you consider this is the force passing by the centroid, okay, it will be at 2/3 from the extremity and 1/3 from the base. So this distance, this 1 second, guys, please. Okay, so you have this distance should be 2/3 of the height of the triangle, and from the base you have 1/3. Okay, so from O the distance is 2/3 times 4. So 2 times 4/3 equals to 8/6, which will give you 2.67. Okay, so until now what we did is that we reduced the rectangular load into 1/4 and the triangular load into 1/4, but we are not done yet because they asked to reduce to one equivalent force. Okay, but of course from now on it's easy for you because you know how to reduce a system of forces into one single force. So once I have this figure, all I have to do is now to calculate the equivalent force of these two, which is equal to their summation, okay? Because they are same direction, same sense. So F equivalent will be equal to F uniform plus F triangular. 160 plus 80 equals to 240. Now the next step is to find the resulting moment about O. What is the resulting moment about O? You can see, you can choose a positive direction. If you consider the clockwise as positive, you have a positive moment for this force. It is plus F triangular, which is plus 80 times the distance here, which is 2.67, and plus the rectangular force times the distance from O, which is 6. Okay, so now this will give you, this term will give you the resulting moment about O. Now, once you find the resulting moment about O, you can say that I can displace my force in a way to produce this moment. Okay, so if I call this distance D, then I should have, of course here I should displace up. Look, of course it should be up because look, your distributed load كلها upward يعني مش منطق تكون equivalent force down. But just you can do this for verification. You know, if you displace up, it will produce a clockwise moment. So the distance D to move up is D times F equivalent should be equal to the resulting moment at O. And as we have seen, the equivalent force is 160 plus 80. So I multiply by the distance which I should move the force in order to get the same resulting moment about O. This equation will give me what should be the displacement distance in order to have same effect about O. Okay, any question on this? Okay, so this is all for this chapter. Okay, we will start together to continue the review problems on undistributed load. Yeah, I will open a new session because this one will end soon. Any question before I close this session?
All here.
Okay, yeah, we'll open a new session.